We're going to start section 5.1 today. This is addition and subtraction of integers. In particular, what you're not going to see in this section that will be maybe mostly related to your presentation that we've kind of been talking about a little bit, is you're not going to see any application questions. I'm going to be focusing in this section mostly on models, how to do the process with children. If you're curious, like where does this fall in terms of sequencing for children learning mathematics, you're looking at upper elementary school, usually around 5th to 6th grade. I know that doesn't hit all of you where you want to teach, but that is where you'll see it occurring in most curriculums. So just so that you're aware, we're going to take a look at some ways of adding and subtracting integers. But before we can do that, we better decide what integers are. So integers are the positive and negative whole numbers. Your book uses the letter I for integers, and you might think, well, of course it does. Why wouldn't it? Well, usually books don't. They usually use the letter Z. And I just bring it up because if you're using a different resource and you see a Z, I want you to realize it's the same thing. Your book uses I because I in integers is the first letter, but most books use the letter I for irrational. Or they just won't use it at all because there's this sort of, like, which one should it be for? The Z is coming from, I think it's Latin. Don't quote me on that, but I think it's Latin for the integers is where it comes from. But either which way we look at it, we're going to put a dot, dot, dot. And these are the numbers like -3, -2, -1. We do include 0, 1, 2, 3, and so on. Basically, we're just expanding our view of the universe of numbers, if you will, by putting the additive inverses in, the negatives of the things that we already had. And this usually comes about by some child at some point asking you, well, what if I do 3 minus 5? And when you're really little, some teacher says, well, you can't do that. We don't have a number for that. Something like that, because we're really not talking about it in 2nd grade, right? We're not doing our addition or subtraction in a way that we would end up getting negatives. But as we continue moving through mathematics, those things become reality. So I want to show you several different models for addition. If you have any colored pencils, I see highlighters, markers with you, something that's got another color, or even just like a pen versus a pencil, it will be helpful for you to have 2 different writing utensils or marking utensils to do what we're going to do, okay? On the first one. It's actually the top on the first one. All right, our first model is called a CHIPS model. And like some of the other models that I've shown you, we're going to draw the image, but if you were really teaching this in class, you would actually use something like poker chips. And they probably wouldn't be called poker chips because that's sort of like one of those things you don't use the word in class, right? The word poker, that's gambling, it's really bad. But you would use chips that looked an awful lot like poker chips, okay? And you can even get these from educational supply stores. There are some versions of them where you just have chips that are, usually they're red and black. So you'll have red chips, you'll have black chips. Or you might have chips where they're red on one side and black on the other. And maybe they don't even use those colors at all, but those are usually the colors you see are red and black. Okay, so I'm going to change my colors on my screen so that I have black and I have red. Okay, so the black chips, whatever color you're using, call it black, are my positive chips, okay? Black is a good thing, all right? And the red chips are my negative chips. I mean, and if you've used like an Excel spreadsheet too much or something like that, black and red are used there as well. We talk about being in the black or in the red, meaning that you're like your checking account being, like a positive value in it. Yeah, you have money, or a negative account, which is really bad, and it means they start giving you, like fees and stuff. Don't do that. So black and red are used sort of in this common sense in the financial world anyway. And what we're going to do is we're going to draw a circle. Okay? And inside of our circle, we're going to insert chips that look like these things. So I'm going to change so that I have, hang on just a second. This says I have 5, as in the positive 5. So I'm going to put 5 black chips in my circle. You can put them anywhere. It doesn't make any difference. And then you're going to do 5 red chips. Not 5, excuse me, 3 red chips. Because it says I have -3. And then what you're going to do is you're going to group them together if they do. Let me do this. In pairs. Now when you group a positive and a negative into a pair, we call it a zero pair. And a zero pair means that it adds to nothing, right? Yeah. A positive and I have a negative, they balance each other out, they add to nothing. So in this case, I actually have 3 zero pairs that in some sense sort of cancel each other out. And if I were to redraw the circle with what I've still got remaining, what would I have remaining in my circle? 2 black chips. And that would represent what number? The number 2. And when kids are actually physically doing this, they would take a black chip and a red chip and they would remove them simultaneously. They're removing a zero pair. And in the end, they have 2 black chips left on their desk in the circle, whatever your description is, and that's representing the number 2. A charged fields model is almost the same as this. You don't need colors for it, so in some sense that's kind of nice. This would appeal maybe more if you were thinking about positive and negative charges of things, electricity, stuff like that, what they balance out. So you know how when you do the batteries, you got the positive end of the battery and the negative end of the battery, that kind of stuff. If you do magnets, you've got the positive end of the magnet and the negative end of the magnet in terms of drawing and repelling things. And what you do is you simply let positives be for the positive numbers. So I have 5 positives, and then I have 3 negatives. And again, I'm looking for things to balance each other out. Let me move that positive because it's in the way. And I'm sort of grouping them together in these zero pairs, right? And if I have a zero pair, they get removed. And when I'm all said and done with the problem, I have left 2 positives representing the number 2. Okay, so I don't know about you, but those 2 models don't really feel that much different to me. The first one's a little bit more concrete. You're probably going to be actually physically using poker chips or some kind of a chips to do it with. The second one's a little bit more abstract, but they're awfully similar. The next 2 models are quite different, however. The next model is called a number line model. So you're probably going to have some children in your class somewhere along the way who don't know how to sit still very well. Have a child like this, right? They like to be moving around. And this is a really good model for a child who is a kinesthetic learner or simply who likes to move around as they learn. So if you imagine putting, tape on the floor, you can physically do this, okay? We're going to draw a picture for it, but imagine putting tape on the floor. And I'm going to show you what this looks like with our desks as the markings, okay? So if a child were doing the tape on the floor thing, they're going to do what I do. This says that I'm going to have positive 5, which means I'm going to move 5 desks forwards. This is 1, 2, 3, 4, and 5. Okay? And then it says -3. I'm going to go 3 backwards. So I'm going to go 1, 2, 3. And what I look at is how far am I away from where I started? And I'm 2 away. So my answer is 2. So in terms of a picture for how you can draw this, let's do that next. We can draw a number line. And we need to mark the number 0 as our starting point on there somewhere. And we don't want it on the far left because we can go backwards, right? I mean, we can go from 0 and we can go left. Those are my negative numbers. But this one, we're moving 5 forward. So here's 1, 2, 3, 4, and 5. So we move forward 5. And then I'm going to move backward 3. So I've got 1, 2, 3 backward 3s over here. If you want to draw your arrows where you're sort of jumping like this, you can do it that way. That's more sort of in line with what a child would really do if they were stepping out the steps. So if that sort of makes more concrete sense, that's totally fine. And the question is, where do you end up? And because I'm on the right-hand side of 0, it's a positive 2. If I had a problem where I ended up on the left-hand side of 0, I would have a negative value. So this works really nicely when we're thinking about a number line, walking, movement, that kind of stuff. The next model It's called a pattern model. Believe it or not, maybe none of you are this way, but there are children who think in patterns. And pattern models can be very efficient, very effective for those kinds of kids. So I want to show you what a pattern model would look like for this. Basically, we want to start with something that we already know, that is adding two whole numbers together. So I'm going to start with 5 plus 2, because 2 is not that far away from a negative 3, right? But it's still two positive numbers. So what's 5 plus 2? 7. And we're going to just keep going down with our 2. We're going to keep doing 5 pluses. What's 5 plus 1? And then 5 plus 0, 5. Now all of that is whole number addition that we've done before. What I'm going to do then is I'm going to put in what happens next. That is, I'm going to decrease that number, that second number, until I can get down to the negative 3. And what I want to recognize is that there's a pattern over here. The pattern is that it goes 7, 6, 5. Well, if the pattern continues, what would come next? 4 and then 2. So 5 plus negative 3, looking at patterns, would also be 2. All right, so thinking about distances away from 0, I'm on the right-hand side, I'm on the left-hand side, leads us to our next topic. Our next topic is absolute values. Now, absolute values really are distances. It's a distance away from something, and distances are always positive. So if you take a look, this definition at first glance looks weird. It looks like I'm telling you there's a positive here and a negative here, and one time the absolute value is positive and one time the absolute value is negative. It's not really what it's telling you. The negative that they're using on this one can be best thought of as the opposite of. And the reason it's the opposite of is because what does the disclaimer at the end, the condition, say is true about x on that line? It's less than 0. It means it's negative, right? These are negative numbers. So if you take the absolute value of a negative number, then the answer is the opposite of that negative. And what's the opposite of a negative? Positive. So that's all this is actually telling you, is that when you have a negative, you're going to do the opposite of it. And that's notationally, in terms of mathematics notationally, how we would write that. The opposite of something would be the negative of it. And in this case, on this line, we're talking about the opposite of a negative number. Now the first line's the easy one. Absolute value of positive number is just the number itself. So this line, the top one, it didn't cause people any problems. But the second line looks odd. It does. It looks odd. We're going to do a few true-false questions related to absolute values next. I'm going to let you just try your best at these for a second. Write in pencil if you're concerned that you're not answering it correctly, and we can erase later or mark it out. It wants us to classify each of the following as true or false. Again, if it's true, it doesn't say you have to do anything. If I were asking you the question, I'd ask you to give me some kind of a justification for why you believe it's true. So you might think about that. But it does tell you that if it's false, you need to show a counterexample. And remember, a counterexample is an example showing a single case where it doesn't work. So I'd like for you to take just 2 or 3 minutes and do your best on A through D, deciding is it true, is it false, and why. All right, let's take a look at each of these, thinking about if they're true or false and why we believe that's the case. On the first one, it says the absolute value of x to the 4th is equal to x to the 4th. So what do you guys think? True? It is true. That's a true statement. Why do we believe that this is true? Yeah, x to the 4th is always greater than or equal to 0. It just is, because it's an even power. So no matter if x is positive or x is negative, when you raise it to the power of 4, you get back a positive number. What if x is 0? Yeah. it still works, right? X is 0, 0 to the 4th, excuse me, is still greater than or equal to 0, so we're still good. Okay. How about part B? Okay, Sally says it's false. Do you have did you say it was false?
Well, because since you said that since it's an even exponent up there, if it's an odd exponent, it's going to make it negative. So I plugged in -3 just to show it to myself, and it ended up being negative 243.
Okay, so yes, there is a counterexample. There's lots of counterexamples. Even versus odd powers, different things happen. Odd powers have the ability to actually give us negative numbers, right? And so here's an example. If x is -3, and we take -3 to the 5th, we get -243. But if you take the absolute value of -3 to the 5th, that will be the absolute value of -243. And what's the absolute value of -243? Positive 243, right? And these two are not equal. And in fact, a counterexample could be any negative number and make this fail. Any negative number would make this fail. Now C and D almost sound like they're alike. They're not exactly alike. They're slightly different. C says absolute value of x is not negative. That is true. And if you want to talk about or think about why, Abby, you were pretty sure of yourself. What were you thinking as your reason for why you thought that was true?
Because it's not negative, meaning that it's either positive or it's 0.
Yeah. So distances have to be either positive or 0, right? I'm either in this classroom or I'm really close to it, but my distance away from it has to be something that's either positive or 0 away. So that is a true statement. How is D different?
It includes, or it doesn't.
Yeah, this one would actually be false. It's sort of like by technicality. It's technically false because what's your counterexample? 0. Yeah, so the counterexample here, the one weird case is if x is equal to 0, then obviously the absolute value of 0 is 0, and 0 is not positive. It's neither positive nor negative. So it kind of gets to be false by technicality. Yeah, I don't know another way to say that, but yeah, there's just sort of this weird case with the number 0. We're going to do properties of integers. You're going to see most of these properties are just like the ones that we had before. We have an extra property that comes up, but let's look at the ones we've had before. Let's see if you remember what the properties are. Closure one is the one that always trips people up because it doesn't look like the other ones, I think. What does the closure property say for the other numbers? Do you remember it? That's part of it, yeah. It says that if you add, in this case because these are additive properties, that if you add numbers from a particular problem set, that you get another number like them. So when we add two whole numbers together, we get another whole number. We did even numbers. When you add two even numbers, we get an even number. We talked about the fact that odd numbers don't work like that. So the odd numbers are not closed. Odd plus odd does not equal odd. But it does work for integers. Add two integers together. So if you have A, B, and C integers, like it says at the top, then A plus B is a unique integer. So there's that part that you mentioned, Hannah, about being unique. You get a unique integer out of that. What's the commutative property look like? We've seen it happen a dozen times, it feels like now. Not really, but a few times. What is commutative? Okay, can you give me an example with maybe some numbers?
Like -3 plus 2 is the same as 2 plus 3.
Okay, so we're doing addition. So if we were to add two numbers together, like A plus B, I'll use generics, that's equal to B plus A. It worked for whole numbers, and it also works for integers. What's the associative property look like? Yeah, we move parentheses. Instead of actually physically moving the numbers themselves, or in this case, I know I'm writing down letters, but we move parentheses around. And we need 3 numbers to do this with, or it's not going to make any sense, right? Associative property is associating numbers together in groups of 2. So I need at least 3 numbers here. So if I have an A, B, C, and I group A and B, it's the same thing as having the A plus B plus C, and instead grouping the B and the C. And the grouping symbols simply tell you what you do first, right? Order of operations kind of stuff. So this is saying if it's all addition, the order of operations doesn't matter. You can group the first 2 numbers together, you can group the last 2 numbers together. If you have 6 numbers, you can group any 2 of them together, and it's going to work in all cases. D is a property that we have seen before as well. Okay, what is the identity property of addition? What does that mean? It's 0. In fact, some of you are still working on test questions related to identities. Do you remember that test question? Yes, you do. That was a very strong yes there, Alyssa. All right, so the identity property says the following, that 0 is our additive identity. It says that if you add it on the left, or if you add it on the right, what happens? It's always still A. And we call 0 the additive identity. All right, we have a new property now. So flip your page over and we'll talk about the new property we get because we have integers that we didn't have before. The new property that we get is called the inverse property, particularly the additive inverse property because we're still working with addition. For every integer a, there exists a unique integer negative a, or the opposite of a, and it's called the additive inverse of a, such that a plus negative a, or negative a plus a, is equal to 0. Why did we not have this with whole numbers? Say it louder, Sally.
We didn't have the negative.
We didn't have the negative numbers to talk about, right? Once we've got the positive and the negative side of the number line, we have this property. And it doesn't even just work for integers. I know we're only looking at integers in this section, but it works for all whole number or all real numbers, right? The opposite of pi is negative pi. They add together to be 0. So we get it for all kinds of numbers. Specifically right now we're looking at integers. Another theorem that we get, another property, is in theorem 5.3. Talking about numbers, if we have 2 negatives, so like negative negative a, we would say this is the opposite of negative a. That's equal to a. There's a very, it's like in the 80s, so at this point I think I can say a very old movie called Stand and Deliver. And there's a teacher in there, and he's trying to drill into his kids that a negative times a negative equals a positive. And that's much like what's going on here. There doesn't sort of seem to be like multiplication, and we aren't technically talking about multiplication, it's just grouping symbols, but it's the same kind of an idea. The negative of a negative, or the opposite of a negative, is equal to a positive.
Would that be the same as like -1 times?
It would, yes. There's an understood -1 in front. That's another way to interpret the same thing. You're correct. The second one, part B, actually talks about a property that we've had before. We did this when we looked at equal addition, for one. We talked about adding something to 2 numbers and it not changing the value. This is a variation of that, but it's telling you that if you have 2 numbers that are the same, A and B, they will still be the same when you add the same value to them. So for example, my 2 daughters are almost identical in height right now, which is kind of crazy for the older one. If you're an older sister, you probably think that the same thing when your sister gets to the same height as you. So if I put my 2 daughters next to each other and they're virtually the same height, then if they both put on 3-inch heels, what's going to happen? They're still the same height, right? That's all this property is saying, is if 2 values are the same to begin with, no matter how they're expressed, if I add something to both of them, it doesn't change the fact that they're still equal. All right, and then the last one says that if I'm adding negative A plus negative B, it's the same thing as adding A plus B together and then putting the negative on the quantity as an ending result. So in some sense, you could talk about sort of like factoring out the negative or undistributing the negative from the left-hand side moving to the right-hand side, and you would have the same quantity.